We have seen the famous transaction problem, and we understood why it is actually happening in a parallel execution world in a multi-threaded system, and we found a mechanism to solve the problem. So we are not going to allow parallelism everywhere. So when we identify there's a critical section in a code, we are going to leave the critical section. We are going to enclose the critical section with the lock. So we make sure the critical section is going to be executed by one thread at a time. The critical section has to be sequential. So that is a fundamental idea here. So if you see the problem in this method is the critical section becomes the bottleneck. So bottleneck means you all know right now the what is happening in Strait of Hormuz. So there is a big ocean before Strait of Hormuz and big ocean outside Strait of Hormuz. But in the Hormuz, that particular 40-kilometer strait, you cannot send multiple ships in parallel. So even though there are 200 ships before the Strait of Hormuz, they have to go in a queue. They have to go one at a time via the Strait of Hormuz. And after the Hormuz, again they can go in parallel, right? They can go side by side with each other. But you cannot do that in the Hormuz. So the Strait of Hormuz is a bottleneck. Similarly, in this case, the critical section, this place, the data, the instructions between the lock acquire and lock release is critical section, is a bottleneck, because even though there are 10 threads coming parallelly, but when they want to buy, it is like the ships wants to cross the Strait of Hormuz, they have to go in a sequence. They have to go one at a time. So when one ship is going, other ships are waiting there, right? So similarly, when one thread is actually executing the critical sections, other threads are waiting. When second thread is executing this, remaining threads are waiting. So it actually increases the overall waiting time. That's what we have done. We're calculating the waiting time. So here we start the time. What is the current time when we are entering into the buy operation, and then we try to acquire the lock. So this actual lock, this particular thread will get the lock if the lock is available, if nobody has acquired the lock. If the lock is acquired by somebody else, it means the lock is not available. The code will not come back. This function, the thread will be in the waiting state. So the thread will come out of the waiting state only when the lock is available, the lock is acquired. So anytime after this particular call, at line number 67, we can safely assume the lock is acquired. So that is made sure by this particular function call. This particular function called the acquire function will let you acquire the lock immediately if the lock is available. If the lock is not immediately available, the system goes to, the thread goes to a wait state. The thread goes to sleep mode, and until the lock gets available, the thread will not wake up. When the lock available, then only the thread wakes up. So at this point, we can say the lock is held. Suppose if Bob wants to buy when Alice is already buying, Bob thread will go for sleeping, right? Because it called the function acquire, it is going in sleeping mode. When Alice releases, then only the Bob will acquire the lock. So there is a sleep period, there is a window. The window is equivalent to the Alice transaction period, and we want to calculate it. So that's why before acquiring the lock, before calling the acquire, I am calculating the time, and after the acquire function returns, when I came out of the sleep, I calculate what is the current time and difference between these. This difference is going to tell me what is the wait duration, how long the thread waited to acquire the lock. So it is equivalent of the ship, how long it waited in the queue to enter the Hormuz, right? So the ship says to the customs service, I want to enter the Hormuz. They are saying there's another ship waiting there, you keep there, and they make you wait until the other ship in the Hormuz crosses the Hormuz, then they are letting you pass. So moment you spoke with the customs office, I want the lock to be given to me, and moment they let you allow. So the difference between that window is called the wait time. That is what we are calculating here. I am calculating the wait duration, and I am adding that into a global variable called total wait time. So this is a global variable. Yeah, you can see here it is a global initiated to 0, and this is calculated at every thread. When a thread wants to buy a particular phone, if the lock is immediately available, the wait duration will be 0, so the wait time will not be updated. If a thread goes into wait mode, then only the wait duration will be non-zero, and whenever it is non-zero, it is going to increment the total wait time. So with this method, with this locking method, we should see how long it actually took for the execution. So the previous execution, if we take, the total lock wait time is 243 seconds. Put together all the threads. So it doesn't mean the program ran for 243 seconds. The program actually ran for 50 seconds only. So this actually calculated using another function, like this is that Yeah. Total runtime is current time and start time. Start time is calculated at the beginning. You can see start time is calculated at the beginning here. So the program actually ran for 50 seconds, but there's a possibility of two threads waiting for the lock, right? So for the Strait of Hormuz, there are 5 ships want to cross. When the first ship is crossing, all the 4 ships are waiting. When the second ship is crossing, 3 ships are waiting, right? So the total wait time, as long as the first ship is crossing, the wait time times 4 ships, and when second ship is crossing, wait time times 3 ships. So totally how long each ship put together waited here, how long each thread waited for acquiring the lock is 243 seconds. So you may not able to understand immediately what is the gravity of this one, but when you actually use that, when the user is in the wait queue, there is a possibility user may go to another e-commerce platform. There are competition, you put them on wait, you are saying the wait time is another 15 minutes, user will try to see, like, he will be bored, right? He will not be just sitting looking at your phone e-commerce page. You have to engage him, and he wants to buy the phone until the stock gets over, because he will be in a hurry. The product may not be available because it is a flagship product, not available immediately. So what he will do, he will immediately go to another platform, he will try to buy from there. If he buys from there, he will cancel the transaction here. If you cancel transaction here, you are going to lose it. So you don't want that to happen, right? So somehow we have to reduce the wait time. So what we can do? So what we have done in the current code, like in the current solution, is the entire buy operation. What is that? Let's close the main. The entire buy operation is logged inside. Why? Because when inventory is being processed by Alice, I don't want inventory to be read by Bob. Makes sense. But if you notice one thing, when Alice is buying a Pixel 10 Pro, you can let Bob to buy iPhone 17 Pro, right? Because Alice is updating inventory of Pixel 10, not iPhone 17. So Alice action is not going to affect the inventory value of iPhone 17 Pro. So instead of making the entire buy section into a single bottleneck, let's create 3 separate bottlenecks. One for iPhone 17 Pro, and one for Pixel 10 Pro, and one for Samsung Galaxy S25 Ultra. So think of the Strait of Hormuz. Instead of having a single path, we are creating 3 different pathways. One for Asia, one for Africa, one for United States, America side. So there are 10 ships, and each 10 ship wants to cross that Hormuz. You are asking which way you want to take. If there are 2 ships wants to go to Asia, only those 2 ships are going to wait in the Asian queue. When one ship is crossing the Asian queue, if a ship says I want to cross Africa, you are going to let it pass in parallel. It is an analogy, maybe not possible in Strait of Hormuz, but here, because the inventory action on iPhone 10 Pro is not going to affect inventory action on Pixel 10 Pro, we can actually create 3 parallelism, 3 bottlenecks, one for Pixel 10 Pro, one for iPhone 17 Pro, and one for Samsung Galaxy S25 Ultra. That is what we have done in this particular program. So initially we had a single inventory lock, right? So in this, if you see, there is a single inventory lock, but now I am declaring it as a Python dictionary. It is not going to be a single lock. So for every phone in the inventory, I am creating one independent lock. So this is going to run, there are 3 phones in the inventory. You can see there are 3 phones in the inventory. So for every phone in the inventory, for 3 times, I'm going to create 3 different lock objects, and I'm going to store that into the inventory lock dictionary. The key value is going to be the phone name. So there's a lock for iPhone 17, a lock for Pixel 10 Pro, and a lock for Samsung S25 Ultra. So 3 locks I have created here. It is the first difference. And second difference, if you see in the buy section, when I'm going to acquire the lock, where is acquiring the lock? Yeah, acquire the lock acquire. So let me put it here. Lock. Why this is separate? Phone lock. We put it here. This is the lock acquire, and this is the lock release. Where is the lock release? Oh my god. For this. So this is the intermediate lock release. This is the final lock release. Okay. So line number 101. So here we are not acquiring the lock, the global inventory lock, the big lock. So instead, we actually take what phone user wants to buy. We take the phone, and then we find the corresponding lock. The inventory locks is a global dictionary. Inside it, every lock is actually stored into the key of the phone name. So inventory locks of phone is the lock corresponding to that particular phone. If it is Alice thread and Alice wants to buy iPhone 17 Pro, then this lock is lock corresponding to iPhone 17 Pro. And this thread takes iPhone 17 Pro's lock. Okay, and this is the critical section until the lock is released, and this critical section will be executed on a thread which is going to buy iPhone 17 Pro. In parallel, there is another thread, an Eve thread wants to buy Samsung S25 Ultra. So at that time, we are going to get the lock which is corresponding to Samsung S25 Ultra, and we are going to acquire the lock because Alice thread acquired only the iPhone's lock. The S25 Ultra lock is free. So the same code will execute in Eve's thread, but for S25 Ultra, it is okay, right? Because Alice is going to update the inventory of iPhone 17 Pro, and Eve is going to update the inventory of Samsung S25 Ultra. So they are not overlapping. So you are actually letting them run in parallel. So let's run this code and see how it is going to be beneficial for us. Okay, let me open one more terminal to compare them side by side. So, okay, Python, e-commerce. I have not run the directory. Should go to the code, multi-threaded e-commerce, Python, commerce with Granular. Okay, I'm running. Okay, Alice wants to buy iPhone 17 Pro. Parallelly, Frank wants to buy Pixel 10 Pro. And Charlie wants to buy Samsung S25 Ultra. And after Alice purchases 17 Pro, then Bob wants to buy 17 Pro. So if you notice here, when Alice wants to buy iPhone 17, nobody else. So every pink lines are specific to iPhone 17. You can see from Alice wants to buy to Alice purchased, there are no other pink lines. So it means when Alice is processing the transaction, nobody else is trying to buy. Nobody else is in the critical section of buying iPhone. But Frank is buying Pixel 10 Pro. His transaction initiated. When Alice and Frank are buying iPhone 17 and Pixel 10, Charlie started buying S25 Ultra. So 3 transactions going in parallel. So you have 3 lines of bottleneck. So 3 parallelism. And based on the phone they are trying to buy, that thread is getting executed in that particular channel. So naturally, after Alice completes, Bob was all waiting, and Bob lock acquired, and Bob wants to buy iPhone 17. Frank completes purchase. When Frank is purchasing the Pixel 10 Pro, Grace was waiting. So moment Frank releases the lock, Grace acquires the lock, and Grace started buying. And Charlie complete transaction. Immediately Eve was waiting. Eve acquired the lock, and Eve started buying S25 Ultra. So you can see the wait time. You waited 7 minutes, 7 seconds. Grace waited 5 seconds. So total wait time. So okay, before going into the wait time, we have to see whether did we oversold or not. Okay, we sold 2 Pixel 10. We had 2 in the initial inventory. No problem. We sold iPhone 17 2. We had 2 in the initial inventory. Completely fine. Same for S25 Ultra. We had 3 in the inventory. We sold 3. Very good. This lock didn't create a problem. It actually didn't oversell the products. We have to see what is the total wait time now. So the total contention wait time is only 59 seconds. If you see the previous program, the course log, every thread put together waited for 243 seconds. And the entire system, the entire program ran for 51 seconds. But here if you see, the entire program ran for only 26 seconds. It is a 50% increment, 50% performance better. And from 240 to 59, the almost 60 seconds waiting time, it is like 1/4, right? So you can learn the concept of a lock or mutex or the parallelism, but how to use that in the real product, that is actually making the difference. You can simply propose, okay, let's introduce a lock. You solve the problem. Somebody will ask where to put the lock. What is the granularity of your lock? If you don't know the real problem, if you don't know the intricacies, you cannot able to answer. You cannot able to think through that. So we had a problem of the universal transaction issue. A book pack answer, immediately put a lock over there in the critical section. You solve the problem. We have done that, but actually it is not the optimal solution. To know what is the right optimal solution, you have to understand the problem better. You have to understand the details. Why a lock, what a lock is doing, what is actually critical section, what is a bottleneck, all these things you should know. Then you will find, okay, there is a independence on the inventory side. So we don't need to put a lock on the inventory altogether. Instead, we can put a lock on one particular mobile at a time. We can put inventories at one particular time. And I'm not saying this is the final optimization. There are even more better optimization. You can even have multiple channels for multiple phones. So some people will have multiple batches. So it is a real solution. Maybe you go to Flipkart Big Billion Day, people are buying in millions at parallelly, right? In single second, the transaction will reach 3 million, 2 million transactions per second. I have been in Flipkart, I have seen how the graph goes. Like we will be there when the 12 o'clock mark hits, when the sale opens for a particular product, suddenly the API hit rate will start going up high, and we should be well prepared to have enough machines computing all those things. Even though we have multiple machines, I'm from an infra team, I'm from IAS team, so I have created multiple machines, I have deployed to the customer team. But if they didn't actually use a proper granular lock, they used a single ghost lock for the entire inventory, even though there were parallel machines, it will be a bottleneck. Only one machine at a time will be handling the transactions. That is not going to scale. Definitely user will see some problem. Immediately what you will see, the next moment, thousands of tweets, thousands of Facebook messages, thousands of customer calls. Everyone will complain about performance issue. The performance issue was not actually a hardware problem. We created enough parallel machines, enough parallel threads, but some guy who didn't understood the intricacies of lock mechanism, who simply imagined, okay, adding a lock is going to solve the parallel problem, he simply put a coarse lock and that became a bottle. This can happen. This has happened multiple times. So now you have to break down the lock into granular level. You may even break down the batches into multiple batches, multiple DCs, multiple fulfillment center, and based on that you are going to put a different bottlenecks, different channels for each transactions. So there are multiple ways. Like this is a very simple example I have shown you. So let's just stick with this right now. So we have seen a transaction problem. We wanted to parallelize to give better user experience, but actually the problem was wrong. The program was wrong. It was overselling to the users, and later we introduced a lock around the inventory. It solved the problem, but actually the user experience was not so great. So we did a simple optimization which actually improved user experience almost 300 times, 300%, right? So it came from 240 to 60. So that is the, definitely it is worth for a simple optimization. So these are the examples, and if you think, if you can able to find a better alternative, can you able to tell me in the comment, is there a better way to optimize the granular lock code to further reduce the wait time? I don't want to have 60-second wait time. Can we reduce it to 30 seconds or even 40 seconds? If you can able to do it, that I can clearly say, or you can proudly say, you understood the concepts. And that's what we need. We don't need people who knows what is lock, what is thread. We want people like, not we means like the companies, the Fang Mang, big MNCs company, who understands the concept and who can able to apply the learning to the right problem and solve the problem in the best possible way. Solving a problem alone is not going to be beneficial. You have to solve the problem in the best possible way, so your users are going to get an absolute best experience. Hope you like the video. Please don't forget to give a thumbs up and share this with every other friend who is trying to learn DSA, system design, and grow in their career. So who is investing on themselves, this is a channel for them. And please subscribe if you don't subscribe yet. Thank you for watching.